Hi everyone. This is the next video after me pretty much explaining a lot of on how to pretty much design a program and how to develop it in time. And this is pretty much me carrying onwards with the quadratic equation example I introduced in the previous video. So hopefully everyone already has taken notes and to be able to kind of like follow along with this video, and I will pretty much do all of my work in this development environment. Just remember, any development environment can be pretty much uh it is always going to be different, but the source code should always be the same, especially if it's nicely written source code. So for this example, yes, pretty much, to reiterate, to remind ourselves of what the quadratic formula looks like, it pretty much ends up looking like x equals uh, negative b plus or minus the square root. In this case, square root is pretty much a shorthand version of, yes, pretty much saying the square root of b, b squared minus 4ac all over 2a. And I'm just double checking and make sure that all of my parentheses are correct. The parentheses are only really important when it comes to pretty much making sure that the that like my order of operations are correct. I'm always aware of where and when I pretty much end up putting parentheses in math equations just to pretty much denote the order at which they should be executed. And just kind of like, keep moving on. Another important factor is the discriminant, which is equal to b squared minus 4ac, pretty much and everything that's inside the square root. So this is pretty much the discriminant. I place it down here just for reference, and to pretty much, just to move on, a good programming habit of mine is I always try and figure out ways on how I can break things down into manageable pieces of code. And in fact, this will be a topic I would like to cover uh, in a future video, possibly the next video, just to pretty much describe a much more in-depth methodology on how I kind of like approach to problems. But a really good approach is what I would like to call the divide and conquer approach, and this pretty much ends up involving taking a problem and trying to break it down into its most simplest, pieces. And in this case, uh, the most simplest thing that we can end up doing in this overall equation is pretty much end up being finding a way to calculate this discriminant. So we can start by defining a function called find discriminant, and as parameters, because we know that for the discriminant it pretty much ends up relying on the variables, or the constants rather, the constants a, c, and b, which can be received from the user, and I can just end up putting it as parameters a, b, and c, and kind of like start defining it, and in fact it pretty much goes from there. So I know that for the discriminant we have a b squared term, so we can end up just defining a variable called b squared. That this variable is is local to the function. It cannot be seen by the whole program. It is only seen by the function specifically, and we can just end up setting it equal to b times b. That's pretty much what b squared is. It's just like b multiplied by itself a total like twice. So 1, 2, that's twice. Uh, and once we kind of like, have the rest, because I think b squared is pretty much like the only piece that's actually pretty critical in trying to, yeah, it's pretty much like critical and kind of like doing something uh quote unquote special like this, but for the rest of it we can just simply return b squared minus 4 times a times c, bada bing, bada boom, it's done. And we can end up, kind of like testing this function again with like the going back to the unit testing. And one way we can um, test this function is just by passing it a bunch of random numbers. If we pass it 1, 1, 1, just kind of like do some uh, quick math. So 1 squared is 1 minus 4 times 1 times 1, which is the same, which is going to give us back -3. And yes, real quick, let me envelop this whole function in the print statement. And Python 3 quads.py, yep, -3. Let's do some more additional testing. Let's put in 514. So 5 squared, because uh no, my excuse me, pardon me. Uh our b term is 1, so 1 squared is still 1, and this is going to be subtracted by 4 times a, our a being 5 and our c being 4. And 4 times 4, that's 16. 16 times 5 is going to be a really big number that I cannot remember at the top of my head. Calculator to the rescue. Since I cannot understand basic math, that is going to be 80. 1 minus 80 is going to give us -79. And there you go, -79. I think it'd be helpful to actually, I'm just gonna like outright delete this portion just to kind of like keep my workspace pretty simple. And for this, trying to think of a good comment, because this is like a really simple function that already describes what I'm doing. Uh, I'm just gonna say, yeah, I just figured out a good comment. I'm just gonna put that. That's pretty much already good enough. Just to kind of like show exactly what I'm trying to do. And let's do one more test of, our find discriminant function. So let's go with 2, 5, and 3. So our b term is 5. 5 squared is 25, and we are subtracting that by 4 times a, which is 2 times 3. So 4 times 2 times 3, 4 times 2 is 8, 8 times 3, that is 24. So 25 minus 24 is going to give us 1. And if I run this, boom, I do have a 1. So, I'm confident enough that this function is finally working as intended. Again, it is almost impossible to try and uh, figure out how to do like a really good comprehensive testing. And in fact, at this point I've pretty much only really assumed integers, so why don't we just try something else with floating point numbers. So let's say 1.5, and let's keep that 3. So again, 5 squared is the same as 25 minus 4 times a, which is 1.5 times 3. So the way how I can think about doing this without pulling out a calculator is, I know that 1.5 is pretty much the same as 3 halves. So 3 halves times 4, that's going to be 4 times 3, 12. 12 divided by 2, that's going to give us 6. 6 times 3, that's going to end up being 18. 25 minus 18 is going to be 7. And just to double check, 25 minus 4 parentheses 1.5. And did I mess up somewhere? 25 minus 4 times, yeah, here we go, 1.5 times 3. Yeah, there you go, 7. Uh, so in this case, it worked. Yeah, so we should get 7. And in this case, notice how it actually ends up returning a float, even though it's an integer. And the reason why is because once you start doing uh, arithmetic operations with a float, every single number, regardless of the other numbers you are working with, are integers, it'll always get treated as a float. So now that I'm confident that this discriminant function is working, now we can kind of move on, forward. And another good way, because now we pretty much have like a way of figuring out the discriminant, so we can kind of move on from here. And a good way of moving on from here is why not try and set it up to end up accepting user input. And one way I ended up describing in the previous video is through the input function. And know that the input function is it pretty much receives keyboard input from a user and store and returns that value returned, but it returns it as a string. So input returns anything it receives as a string. So I'm not able to quickly think of a way on how to end up writing a function for this without making things unnecessarily complicated, unless I just got a good idea. And I say a good idea because it's actually kind of clever in the sense that I can end up, doing it as a way of accepting user input. So let's just kind of, say define, user input. We're not necessarily going to pass it any parameters, but in this case, let's just kind of, call a variable called inputs and let it hold a empty list. This is what I'm going to be doing. And in this case, what I'm going to do is uh, kind of like, comment receives user input stores it um, stores it in a list that is returned. So what this function is going to effectively be doing is just accept user input through the input function, store it inside of a uh, empty, initially empty list, and then return that list. And then from there, we can kind of, keep moving forward. And in fact, I can kind of like also call, variables A, B, and C. And what I can end up doing is just kind of like setting it equal to input. Uh, please enter your, please enter coefficient A, and let's just, pretty much wait. But remember, input returns it as a string. So one way we can fix it is just pretty much, uh, convert it into an integer. And you can actually do this to convert things into an integer. And I'll pretty much, keep continue doing this for the rest. Please enter coefficient B. Um, please enter coefficient C. And once I already pretty much end up having my A, B, and C, there's a couple of ways on how I can end up storing it in the list. The easiest way is through the append method, and inputs dot append, and it pretty much will end up appending, all of my, all of these variables that I've, previously defined, uh, immediately right before one another. But remember, this is like three pieces of code, like 3 lines of code that's being repeated. If you have three pieces of, like, 3 lines of code where you're effectively doing the exact same thing a number of repeated times, why not just go with a for loop? So for I in range 3, and this is going to get repeated 3 times. Wait, but I don't think this is going to work now that I think about it. And the reason why is because all of our variables are different. So in the end, it probably wouldn't be. I usually don't like this approach because it's kind of like brute forcing it. But I guess at the end of the day, it's just like a matter of me having to accept the way how it is because of how I designed it. This is pretty much a, I wouldn't say a design flaw. It's just pretty much just, not clever code, if that makes sense. But for now, I'm just gonna, roll with it and kind of, keep going with it. Oh, I almost forgot. We have to return um, the list. So in this case, yes, to kind of like, test it out, let me uh, call a, yeah, declare a new variable called coefficients and set it equal to this user input function. And remember, this user input function returns a list. So this variable coefficients is now going to be a variable holding a list. So let's just clear my workspace real quick and then run it. Please enter coefficient A. Let's go with 2. Please enter coefficient B. Let's put in 5. Please enter coefficient C. Let's enter 3. And, well, nothing happened. And for the most part, that's kind of good. But let's just kind of like check to see if it actually worked by printing out the contents of the coefficient. So again, 253, 253, and it's in the exact order we want. This is good news. This is great. We're, getting somewhere. So uh, now we pretty much have, you know, have all of this set up so far. We can kind of like move forward, and one way we can end up moving forward is quite simply. I shouldn't have deleted that previous list. It's just kind of, coefficients called user input, not in pot. So let's just call it, and let's call a declare a variable d and set it equal to find discriminant, and we have to pass it the coefficients a, b, and c. So one way we can end up doing it is because we know that the coefficient at index 0 of the list is a, the coefficient at index 1 is b, and the coefficient at index 2 is c. And we know that when it comes to 2, 5, and 3, let's just kind of like do the math real quick. Let me just use this again as like a workspace. Yeah, so A is equal to 2, B is equal to 5, and C is equal to 3. So in this case, D is going to be equal to 5 squared, which is 25 minus, here, let me kind of like do it this way, yes, for clarity, minus 4AC, that's supposed to be a 3. 5 squared is 25, minus 4 times 2, that's 8. 8 times 4 is 24. So our D is going to be equal to 1. So when I, calculate this discriminant D and I print it out, I should expect, the value to be 1, and we can test it out. So 2, 5, and 3, we do end up receiving a output of 1 for the discriminant. Perfect. So far, so good. Everything is working as intended. Easy peasy. Now, this is where I wouldn't say things get complicated, but things start getting a little bit more interesting. And the reason why it gets more interesting is because, recall, the discriminant helps to discriminate what type of solution we are looking for. And this can range from either, two real solutions, one real solution, or pair of complex solutions. And this is all based on what the value of D is going to be. Because if you remember in the previous video, if D is positive, two real solutions. If D is 0, one real solution. If D is negative, pair of complex solutions. But how can we describe this kind of behavior in our program? That's the easiest part because in this case, uh, now I'm kind of like thinking about another method of pretty much, implementing a function. And in this case, let's kind of go on about. Right now, I am thinking on how to kind of like do this with like everything we have so far because I know for this we have like a negative b. In a 2a, the discriminant is pretty much what's inside the square root, and we can actually end up working with that. So here, let's call a new function. Uh, let's define, find quad solutions. And right now I'm kind of like keeping the parameter list a little bit empty because I'm just trying to think about, because if you're trying to find solutions to a quadratic equation, obviously you're going to be needing a parameter d, which is going to represent a discriminant, which we are going to pass, and we just need to, test some things out. How can we show that d is positive? Well, so for our purposes or in the purposes of programming, 0 is considered neither positive nor negative. It is just 0. So we can actually end up using an if statement. So if d is greater than 0, this pretty much, uh, d is positive, then, we can test it out. D is positive to check if it's 0, because if it's not positive, then we pretty much just end up having to check for 0. But that's what you think would work. But my suggestion would be, instead of checking to see if it's 0, let's first check to see if it's negative. And you will see why. Print D is negative. And then finally, we just have to check if it's an else statement. So that way we don't have to write any additional conditions. So we pretty much described it. Let me just kind of like briefly comment this function. Um, finds the solutions to the quadratic by checking, by checking the value of the discriminant. Easy peasy. Let's test it out. So we already pretty much end up finding our D. So in this case, we're gonna have to like do a couple of unit tests. At most, it's going to be minimum 3 unit tests. We just have to check whether D is positive, whether D is negative, or the situation when D is 0. So this is going to involve a little bit of me thinking about which coefficients to make use of in order for me to effectively just obtain, yes, to show what I'm trying to show. So yes, real quick, we don't really have to like put a print statement because we pretty much already have like the print statements handled within this function. So we're just gonna like do find quad solutions, and let's pass it our variable d. Let's run it. So again, 2, 5, 3. We should get 1, and 1 is positive in this case. All right, perfect, excellent. Let's kind of like run this again. I'm trying to think of a case where D is going to be negative, and the only way for D to be negative is if our 4AC term is going to be bigger than our B squared term, and the easiest way we can do this with is by setting all of our coefficients A, B, and C equal to 1. So let's do that. 1, 1, 1. And before I press in the final enter, yes, to illustrate, if A is 1, B is 1, and C is 1, our discriminant is going to be 1 squared minus 4 times 1 times 1, which is the same as 1 minus 4, pretty much, which is going to be equal to -3. So let me just press enter here. D is negative, A is shows. And now here's a much more slightly difficult case, and that is to make the whole equation equal to 0. And the easiest way to show this, at least for me, the way how I think about it is by trying to because we know that we have a b squared term. The only way for that b squared term to be equal to to pretty much like cancel out with like the -4ac is if and only if. So let me kind of like put down here uh d is equal to b squared minus 4ac. The only way for these two terms to cancel out is if uh yeah, c is equal to b, a is equal to 1. That's one way of showing it, and I can even do the math real quick. So let's say that our a is 1, our b is 4, and our c is 4, because 4 squared minus 4 times ac, so 1 times 4. So 4 squared is 16, 4 times 1 is 4, 4 times 4 is, guess what, 16. That's going to give us a value of 0. So let's test it out. Let me remember. Yeah, so 1, 4, and 4. D is 0. So boom, we just came up with a quick testing scheme to make sure that the values we are working with will always end up, kind of like be in this kind of range. We just kind of like quickly came up with some unit tests to make sure that so far our program functionality is working as intended, is working as is. So now we kind of like further flesh out, this fine quad solutions. And the way how we can do that is we know what to do when D is positive, because when D is positive, that means that there are two real solutions. And the way how we can do that is simply because we pretty much just have to follow the remainder of this equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Easy peasy. But wait, there's something that we still haven't thought about. So sorry for like the little blip. I am currently looking up something. Here we go. This is what I wanted to look for. Right now I'm kind of like doing some quick Googling. Actually, yeah, this is going to be more perfect this way. So Python mathematical functions, and let me find this square root. There we go. Well, yeah, I square root non-negative. Return the integer square root of the non-negative integer, and this is the floor of the exact square root. Is there other ways? There you go. Returns the square root of x. In this case, notice how it doesn't tell us much more outside of that. We can kind of like I can try and mess around, but it only really says return the square root of x. However, with my experience in programming, I can tell you all that most likely this is going to be returned as a integer. No, apologies. This function is going to return whatever it does as a float and not as a integer. And this is just based on my experience working with other similar math libraries. So in this case, since this is actually in the math module, we're going to have to do a import statement. So import math, and in this case, importing math imports the entire module. However, we only really need, at least to what I believe, we're only really going to be needing one thing out of like the math module. So I'm just going to do from math import square root. Now we have access to it. So if we note that D is positive, we can kind of like implement the rest of this. So let me just call it, disc short for like discriminant or square root D. Yeah. And then all I really have to do is call, the square root of D, and we can kind of like double check with a previous example. I know with 2, 5, and 3, I believe that the discriminant is going to be 1, so the square root of 1 is also going to be 1, and we can test it out. Let me clear this out. 2, 5, and 3. Oh, I forgot to print this square root of D. 253 1.0, and just like what I said earlier, I guaranteed you that the value returned by this was going to be a float, and lo and behold, it is a float. But in this case, I don't mind it being a float. I'm actually okay with it because we're just gonna be moving forward. It's not gonna be something that's gonna give us too many hiccups. And in fact, once we kind of figured out that there's going to be two solutions, we're going to have to add and subtract the square root of this discriminant by negative b. But wait, we don't really have negative b involved. Well, let's just kind of, uh, call, because we are going to be needing both a and b, so let's just kind of like pass as parameters to this function our coefficients a and b, and down here I'm going to have to modify it to pretty much pass it both the A coefficient and the B coefficient. Bada beam, bada boom, we're going to keep moving forward. Over here, uh, I know that I'm going to have to add and subtract all of this to like negative B. So one way to kind of like approach this is we're going to I'm going to call a variable called plus, and I'm just going to, do negative B plus square root of D, and then I'm going to call a variable called neg for negative, set it equal to negative B minus square root D. An important thing to note is positive is not necessarily going to be actually positive all the time, and negative is not necessarily going to be negative all the time. It is just a way of showing that I am adding and subtracting the square root of our discriminant. And with that moving forward, then we have to divide everything by 2a. So one way we can do this is we know we're going to have two solutions. So let's just kind of like call this, root 1 and set it equal to plus divided by parentheses for order of operations 2 times a. And let's go with root 2 equals negative 2 times a. So now we have all of that, and let's just finish off right here with, kind of like showing what exactly we found. Uh, so two real solutions. Uh, root 1, let's set that equal to, let's go with like pretty much like a floating point number by up to like 2 points of precision. I'm not sure if you guys have seen this kind of notation before or not, but it's a notation that I'm really comfortable with, so apologies if it's something you've never seen before, but it's not that like any more complicated than everything else that you guys have done, and I'm just gonna like, complete the remainder of this percent point 2f root 2, and yes, real quick, and let me add in a new line over here. And again, sorry if you guys haven't been exposed to this. It's just kind of like things I'm doing just kind of make things look a lot neater, and you will see what I mean short enough. And now I guess it's time to pretty much completely solve the for the roots of everything. So I think we're gonna be inputting specifically these inputs. So I know that this is gonna be 5 squared, 2 times 3 times 4, so that's gonna be 25 minus 24, making it equal to 1. The solutions are going to be the first solution. I'm gonna like kind of like do this as an ordered pair. The solutions aren't necessarily an ordered pair. I'm just doing this more out of personal mathematical convenience. So the solution for this square root of 1 is just going to be 1 negative b, which is going to be negative 5. Yeah, negative 5 plus 1 is going to be negative 4. Negative 4 divided by 2a. A is 2, so 2 times 2 is 4. Negative 4 divided by 4, one of our solutions is going to be negative 1. The other solution is just going to be negative 5. Wait, I think I messed up my line of thinking. This is supposed to be negative 1. I'll explain later. But 5. Oh, wait, no, it is right. It is negative 1 because negative 5 minus 1 is going to be negative 6. Negative 6 divided by 4 is going to be negative 6 fourths, and that can be reduced down to uh, 3 halves, or another way of kind of like saying this is pretty much negative 1 or negative 1.5 as our solutions, and we're going to kind of see if this is true or not. So 253, and there is an error. Name A is not defined. Oh, yeah. I did a little oopsie here. I pretty much started passing in variables as opposed to integers in our coefficient. So that was at least like, a good, easy error to fix. Let me run this uh, again. 253. There you go. Just as exactly as I calculated in my head. These are our solutions. Root 1 being equal to that, root 2 being equal to that. Great. So now we can actually continue with this approach and start fleshing out the remainder uh, of these solutions. We know one of them is going to be for negative, and when it's negative, then that means that there's going to be, uh, you know, pair of complex solutions. And in this case, this else denotes that it's going to that d is equal to 0, so that means that there's only really going to be one real solution. And let me kind of like do this quicker because it's much easier to implement this real solution as opposed to this complex solution, and I will explain why later. But yes, real quick, it's going to be a similar approach to what we did previously. Let's just kind of like declare the same variable name, square root of the discriminant. Let me just kind of like do this more for like code readability purposes. Square root of d. We know that there's only really going to be, actually in this case, we don't even have to do the square root of d. And the reason why is because d is already 0. The square root of 0 is just 0. So it's kind of pointless of doing it. And we can kind of like easily calculate, the root. I'm just going to call it root. We're going to pretty much set it equal because if the discriminant d is equal to 0, then the answer is simply negative b divided by 2 times a. Easy peasy. So let me just kind of say one, I forgot to do this, one real solution, and let it set it equal to a floating point number up to 2 precisions. That's about enough. And now I think the easiest way to have shown that it was, um, yeah, to show that it would have been 0 is if I go back here, is if C is equal to B and A is equal to 1. And I think the example I use for the coefficients where uh, 1, 4, and 4. Yeah, in one real solution, the root is -2. We can kind of like double check our math on that. So real quick, that's going to be 4. 4 times 1 times 4. We know that that's going to be 16 minus 16, which is just equal to uh, 0. So then negative b, our b is 4. So -4 divided by 2a. 2a is 1. I mean, yeah, 2a is 2 because a is equal to 1. So -4 divided by 2, that's going to give us one solution of -2, which lo and behold, it is our solution down here. Great. But wait, how are we going to be able to take care of this negative thing since we are dealing with complex solutions? Normally, as a rule of thumb, so when I talk about complex solutions, I am talking about um, something that takes on the form of um, yeah, it's going to take on the form of a real number r plus a imaginary number I. That is what I mean by a complex solution. It contains both a real portion and an imaginary portion. Yes, I could go on and talk about why do we even have imaginary numbers, but I believe that that is out of the scope of this whole course. There's a lot of applications for imaginary numbers when it comes to things such as in electrical engineering, especially electrical signals. Electrical engineering would not be possible if we did not have imaginary numbers to work with. It's really difficult to explain, and like I said, this is out of the scope of the class, so I am not going to bother explaining why we bother with imaginary numbers or even complex numbers, but it's still something that I would like to work with. So I'm just kind of like messing around here. Huh. All right, I guess I'm gonna have to like Google it. So Python, because I know that there's a way of representing complex numbers, and for me, it's just kind of like a matter of just googling things real quick for this one, creating a simple complex number. All right, so there is a syntax where we pretty much end up calling a function called complex that takes in a real portion and an imaginary portion. Huh. Mathematical calculations. And I know there's like a C math, which is, mathematical functions for complex numbers, uh, power and logarithmic. Uh-huh. So notice how in this case I can actually make use, like this module does make use of a square root function. And I imagine that this will return a imaginary number as well. So why not, test it out? Let's figure it out. So just uh, real quick, just to go back, since this module also has a similar method called square root. It's gonna cause a conflict. So now I'm gonna have to like uncomment this and then import CMath. Uh, I like to keep things in alphabetical order, and I'm gonna have to like comment this out. I am gonna have to go back to like every instance of square root that I've called before in the past to do all of this, and just to double check that, yeah, okay, so there shouldn't be an error. So let's just kind of like run it to remove all doubts. Yep, there we go. No, that was probably the worst one. So let's go back to our original one. Yeah. So now that I've kind of like successfully done that, I don't have to worry about any kind of like potential errors. So for yes, like for uh transparency, I've never used the CMath the CMath module before. This is actually my first time using it, but I'm just gonna test it out real quick. So let me comment all of this out and let me type in square root of -2, and let's see, not only square root, but I need to do CMath dot square root. So let's run it and see. Yeah, there you go. It does give us a completely imaginary number, and I know that like these imaginary numbers are kind of like given as a J instead of an I. There's a reason why it's J instead of I, but for now we're not going to focus much on that. Let me do something like square root of 4. That should give us a much cleaner number. Yeah, 2J. So yeah, it's working as intended. I'm confident enough that now it's gonna work, especially for like the complex solution. So we can move forward. Hopefully, let me double check the documentation again. First complex number, print. Mhm, mhm. Here, I think another thing I would like to do is yeah, so I can kind of like understand what's going on better. I'm gonna see if this is gonna give me an error. It might actually give me an error since I'm using J, but we're gonna find out. Okay, no error. Good, 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 good. Uh, New test is equal to 1 plus test. Good. And let's print out new test and see if yeah, there you go. Okay, so now I'm kind of like feeling a lot more confident about this. Let me just uncomment all of this and go back up here into the negative. So the reason why I ended up kind of like doing all of that is, and I think the form of this is actually like BI, but I think since the I is actually J, A and B are real numbers. Just kind of like to explain it as. So I'm actually going to be using a similar approach as I did with like when the discriminant is positive, because when it's negative, all I really have to do is CMath square root of uh, D plus is equal to negative B plus square root of D. Negative is equal to negative B minus square root of D. I'm going to call this like C root 1 is equal to plus divided by 2 times A. C root 2 is equal to negative divided by 2 times A. And at this point, I just kind of like realized oops, I'm pretty much copying a lot of previous code. So I'm just gonna like reuse this portion and just kind of like, I did not want to do that. There you go. Thank you. I got fat fingers. C root, C root, boop, boop, boop. And let's go. So I think in this case, it's pretty much a case where uh, we're going to have a negative number, but I would like to work with a negative number that can be easily done the square root of. And the easiest way, uh, the one number that kind of like strikes me out the most is -4, because the square root of 4 is already 2, so we're just going to get like 2i or 2j in this context. So I'm just gonna like be brainstorming a quick test case with like the different coefficients, because I know that the b squared needs to be small enough to be overtaken by the 4ac, but not quite to the point where it's just going to give us a really bad number. So I know that there's 25. That's like 5 squared. Let's keep, what about 1, 1? Or, yeah, this might work. So let's kind of like do this real quick. B squared minus 4ac. So 4 squared is 16. 4 times 2. Uh, that's 8. No, this is not gonna work. So now let me just kind of like make the c into a 3, and now it's gonna work. And the reason why it's gonna work is because 4 times 3 is 12. The b is unchanged, so 4 squared is still 16. 16 minus 12, that's going to give us 4, or rather, no, not 4. Right, it needs to like be able to overtake it, and the only way I can think of would be if it's here. Let's make c5 because 4 times 1 it's 4. 4 times 5 that's gonna give us 20. 16 minus 20 is gonna give us the -4 that I want. So now that I've kind of like, done this calculation real quick, let's kind of just really briefly think up of like our solution set. So in this case, the solution is going to end up being negative b. That's going to be 4, so -4 plus 2j. Yeah, so the first solution is going to be -4 plus 2j. The second solution is going to be -4 minus 2j. Yes, to kind of like show that it should still work for uh, negative numbers. The only thing I'm worried about is probably like, because this is only for like a float number, but this is like a complex number, so I'm not sure how Python is going to show how it's going to do. I feel like it's going to give it an error. I'm pretty confident it will give an error, but we're going to find out. Yep. Oh, there was something undefined. It's because I put down ne instead of neg. So again, going back up here, 1, 4, 5, and 2 real solutions. Why is that? Hmm. Yeah, 1, 4, 5, b squared minus 4ac. Yeah, it should be a negative number. Why is it going to... Oh, yeah, yeah, yeah. I forgot to change this. Yeah, yeah, yeah. And in this case, can convert complex to float. Yep, I kind of figured that that was going to be an issue. Uh, I remember seeing somewhere on here, yeah, c dot real. That's what it is. We got to split it up into different portions. Yeah, no problem. Easy peasy. Um, so it's just gonna be like some additional work. It's gonna be that plus. Yeah, we're talking about root one, and root one's like the positive root, the positive complex root. I should add. Then I can quite easily just do this. C root one dot real, and then C root one dot imaginary. I C root 2 dot real, C root 2 dot imaginary without that additional character. Now let's run it. Going back up, 145. There we go. It works. And do we get what we did not, but that's probably because I forgot to divide it by the 2A. But in this case, yeah, I was like pretty much off by like just that division of like the 2A, which is just gonna be 2. So I'm just gonna like kind of like quickly modify it as this just to show that yes, I am smart and I am qualified to continue doing this. I also forgot to change this from a positive to a negative. And now we pretty much have a fully fleshed out quadratic program that will give us solutions for any type of quadratic that we throw it at. It's going to give us both real solutions and complex solutions.